Alright guys, welcome to part 2 of our study guide here. Let's go ahead. These ones are modeled more after the standard FRQs on the AP exam, so a lot of these questions will look like your AP or your FRQ questions. So we're going to look at two of them. First of all, we have the height of a tree at time t is given by a differentiable function h, where h of t is measured in meters and t is measured in years. Selected values of h are given in the table below. So at 2 years, the tree is 1.5 meters. At 3 years, it's 3 meters. And at 7 years, it's 11, and so on and so forth. This is a differentiable function, which gives us the green light to put into practice a few different theorems, which we learned about this year. So let's begin. Now, part A. This is actually a review question. And I put it in here on purpose because, well, it's a very common question. You can expect to see it on your exam. But also the fact that look how much it looks like this question. Okay, they're really only different by that little prime right there. In calculus, that little prime means a lot. Okay, this is a function up here of h. This is not a function of h prime. So we've done this before in the past. So let's go ahead and review how to do this one right now and see how to do it. Once again, it's worth 2 points. One is the answer, and the other one is going to be to interpret what it means in the context of the problem. All right, so let's go ahead and begin here. So first of all, we're going to apply the fundamental theorem of calculus, which means I'm going to start by integrating h prime. Now, what happens when you integrate h prime? Well, when you integrate h prime, you get regular h. Last time we did this, I noticed a few of you guys didn't change it to regular h at this point. So make sure you do that this time because that could cost you the credit for the problem. All right, and after you've integrated it, it changes from h prime to h, and you have brackets with the numbers over here on the right instead of the integrals. And then to continue with the fundamental theorem of calculus, we plug in the top number first, and then we plug in the bottom number. Now, the table tells us what h of 10 is. H of 10 is 15. And h of 2 is 1.5. And if we subtract those, we get 13.5. So if you got that far, you would get 1 point. Now, you can't just put the answer. You do have to show your work, how you got there, but that would be worth 1 point. Now, what does it mean to interpret? Well, to interpret, you need to do three things. You need to use the units of the input. You need to include the units of the output. And then you need to include the context. In other words, your explanation should have something to do with this story problem about a tree and its height and the years, right? So the input variable, t, is time, and that's years. So our interpretation has to have something to do with years. And our output variable is the height of the tree, and that's measured in meters. And the context is we're talking about a tree that's growing over time. So now we're almost there, but we need to interpret what this number actually means then. Well, h of 10 equals 15. That means that's the tree's height at the 10th year. It's 15 meters tall. Second year, the tree's height is 1.5. Now, if we subtract those, what does it tell us? That tells us how much the tree's height has changed over that time period. The tree's height went from 1.5 meters to 15 meters. In other words, it increased by 13.5 meters over the time period of year 2 to year 10. Okay, so now we're going to write our interpretation, and it's going to have these 3 elements to it. So what we would say is we would say the height of the tree increased by 13.5 meters from year 2 to year 10. And that's it. Okay, so I want you to notice that we have the output units, we have the input units, and then we have the story problem. The number has been interpreted in the context of the story. So that's the second point for this problem, is being able to accurately explain what that is, including those three elements of an interpretation. So step one, do the fundamental theorem of calculus showing your work, and you've got a point. Two, interpret it using these 3 points, and that's your second point. You'll see one of those on your test. And the only reason I'm including this old concept, which we've tested previously, is because it looks so much like one of our newer concepts, which is our next question. But they're actually very different. Integrating a derivative of h is completely different from integrating h itself. Now, on this one, it's kind of nice though, because they actually tell you what to do on this problem. In fact, on part B, they tell you to use a right Riemann sum to estimate this integral. Okay. So we kind of know what we need to do here. All right, so here we go. It's going to, when you're doing a right-handed Riemann sum, the distance from here to here is your base for that rectangle, and you just keep doing that. The next rectangle will have a base of 2. The next one will also have a base of 2. And my next rectangle will have a base of 3. And typically, which I didn't do here, but I should have, is they'll tell you how many rectangles you should have. And as you can see, we got 4. Every once in a while, they'll give you, they'll ask you to do less rectangles than are possible. In that case, you have to break it up evenly. But in this case, that's not going to happen. You couldn't break it up evenly because they don't go by even spaces. So we're just going to stick with what we got. But the problem really should have said, use a right Riemann sum of 4 subintervals to calculate this. But anyway, back to our problem. Our bases are on the top, and my heights are down here. But since we're doing a right-handed Riemann sum, then we're going to start on the right, and that's going to be my height. That's going to be another height, another height, another height. This one is not going to be included. And so we just do base times height, base times height, base times height. Now, I don't know if on the actual AP exam, in fact, I'm pretty sure they would not count what I'm showing right now on this table as work. They wouldn't, because this is not like conventional math notation. This is just how I show it. So on the actual AP exam, they would want to see that you had at least maybe written this out. 3 times 1 plus 6 times 2 plus 2 times 11 plus 3 times 15. And by the way, on the AP exam, it's totally okay to leave it just like that. So you don't even need to go through the process of simplifying it, because what if you get it wrong? If you get it wrong, well, then you're going to lose the point. So just leave it. Just leave it. And that's pretty much good enough. That's going to be worth 2 points on your test. Okay. Let's go ahead and take a look at part C. The question here is the estimate on part B an overestimate or an underestimate? Well, what is our function? So whenever you're deciding whether you are dealing with an overestimate or underestimate, you have to ask yourself, are you dealing with a right-handed sum or a left-handed sum? You also have to ask yourself, is your function increasing or decreasing? Now, on this problem, to tell whether your function is increasing or decreasing, you look at the y values. As we go from left to right, the tree is getting bigger, right? The tree is getting taller. And therefore, this is an increasing function. So I know that if I were to graph this, it would have an upward trend to it like that. So I know it's increasing. Now the next question is am I doing a right-handed or a left-handed sum? Well, as you recall, we did a right-handed sum. So that's here. So what we're looking at then right now is we're looking at this particular scenario where we have an increasing function, and we're doing a right-handed sum. So now here's how you could use your notes if you want to, but here's how I do it, because I don't look at notes. I just think, okay, well, if I started on the right here and started drawing rectangles, what does it look like? like an overestimate or an underestimate? Well, that sure looks like an overestimate to me. And so I would say it's an overestimate. Now, how do you write your answer, though? Because that's very important. You would say the estimate in part B is an overestimate because it is, or because we did a right-hand sum with an increasing function. So you would need to state that your function is increasing. And in fact, it might even be better to say what that function is. Might want to say h of t, just to be safe, because there is another function up here. It's h prime, and they're kind of picky about that stuff. I don't think it would matter on this problem, but just to be safe. So we've mentioned the fact that the function is increasing and the fact that it's a right-handed sum and our answer. So you would need those three elements to get your credit on this. And it should be in a complete sentence. You can't just say right-hand increasing overestimate. You have to explain it. There you have it. So that's worth 1 point. All right, let's go ahead and take a look at part D. Find the average value of h on the interval from 2 to 10. Well, how do you find an average value? We learned that in 6.6. The formula for the average value of a function is 1 over b minus a, and then the integral of your function, h, on that interval. Okay? So in this case, my a and my b would be the 2 and the 10. Okay? So 1 over 10 minus 2. And then bracket, and then the integral. Now, another thing I should have put in here, so I think I'm going to change it and re-upload it. But anyway, I should have said find the average value of h on the interval function using your answer from part B. Or I might have said using a right-handed sum, because you need a way to get this integral. Well, we already did that in part B. We did it with a right-handed sum. So on your test, I'll be more specific and I'll state that, okay, use the right-handed sum, or I just might say using what you got from part B. And so in part B, we got 3 times 1 plus 6 times 2 plus 2 times 11 plus 3 times 15. And once again, don't simplify it. Just leave it just like that. But I do want you guys to know what this is. It doesn't tell us to explain anything, so we don't have to explain it. But I do want you guys to remember what we're doing here, right? Whenever you think of the graph of this function h, okay, maybe it looks like this. Okay. The average value is the average height of your function. So in other words, let's say that height's the average. Now, how do I know that's the average? Because the area above that line is equal to the area below that line that's missing. And what we end up with is a rectangle that has the same exact area as the original shape, but it's just as a rectangle. And so if you know the area of the rectangle, which is the area under the curve, and you divide it by the base of the rectangle, which we know is the distance between 10 and 2, which is 8. If you divide the area by the base, that'll tell you the height. And that height is that average value of the function, the average height of the function. And so it's nice to know what it means. You don't have to do that part on your test, and please don't, because the more you do, the more likely you'll miss something and lose points. We don't want that. Just stick to what they ask. But I did want to take a moment to refresh you on that.
All right, guys, so we're going to take a look at part E. Now, in part E, we're being asked to find the average rate of change. Now, that looks a little bit similar to the average value, but they are different things. So to find the average rate of change, we're going to do the old slope formula here. So that would be h of your final value minus h of your initial value divided by the difference of those two inputs. Okay, so h of 10 is 15, h of 2 is 1.5, 10 minus 2 is 8, and then we're going to go ahead and simplify that. So let me get my calculator here. 15 minus 1.5 divided by 8. And I end up with 1.6875. Now we want to be able to state what the units are. The units, the top numbers, as you guys can see, are meters, and the bottom units, as you guys can see, are years. And so the units for this are meters per year. Now we'll go ahead and we'll interpret this. So what is the interpretation of this one? Well, the input units are time. The output units are the answer units, and that's meters per year. And so what is this telling us? Well, notice I've got a positive number here. This is an average rate of change. And so what this means is that on average, the tree was growing at 1.6875 meters per year on the time interval from year 2 to year 10. So I'll go ahead and write that out for you guys. All right. Here you go. I'll go ahead and highlight this up here for you. And that would be the proper interpretation of that there. All right. We'll go ahead and move on to our next one here.
All right, so there it is. So we tested 3 concepts here from Unit 6. Riemann sums, whether it's an overestimate or an underestimate, and average values. But I included 2 review questions, which will also be on your test, if all goes according to plan. And in order for you to compare and contrast these review questions with questions that look very similar to them, but they are very different. Just getting you guys ready for that AP exam. All right, let's go ahead and move on to the next part now. All right, and let's go ahead and move on to our next question here. The graph of f is given below and consists of a line segment and a semicircle. The function h is this integral function here of f from -3 to x. All right, so our first question here is asking us to find 3 things. Each one of those things is worth 1 point, and so a total of 3 points. So the first thing that we're asked to do is we're asked to find h of -2. And so this is my function right here for h, right? So if I want to find h of -2, I'm just going to be plugging in -2. Now you got to pay attention to whether or not the limits are in the correct order. You want the smaller number on the bottom and the bigger number on the top. In this case, I'm okay. But if they were reversed, you would have to flip them and put a negative in the front using that property 2 that we talked about in lesson 6.3. But as you guys can see, when you plug in the -2, it replaces the x in both of these spots. So it looks like this. And so basically what this is asking us to do at this point is to just find the area under the curve from -3 up to -2. So that would be this little triangle space here, which is an area of base times height cut in half is 1/2. So h of 2 is equal to a 1/2. And since it's above the x-axis, it's a positive 1/2. Okay. Next part is h prime of 2. And for this, we could apply the second fundamental theorem of calculus. When you take the derivative of an integral function, the integral cancels out and the x drops in. And so h prime of t, that shouldn't say h prime of t, I'm sorry, I should say h prime of x. Let me fix that. H prime of x is equal to f of x. Okay, so in other words, h prime is this graph over here. It's not the area under the graph, it's the blue line itself, the graph itself. And so what is h prime of negative 2? They're asking for the actual y value at this point on the blue line, and the y value at that point is 0. Next, we're going to find the second derivative. So the second derivative of h is going to be the first derivative of f, right? Because if this is true, right? Taking the derivative on this side gives me the second derivative. Taking the derivative on this side gives me the first. So the second derivative of h is the first derivative of f, which means that h double prime is the slope of f. So if they're asking me for h double prime of negative 1, what they're really asking for here is they're asking for what is the slope of the line on that graph at negative 1. So negative 1 is right here. And so we're on this straight line here. So we could calculate the slope by just looking at the rise and run. It's down 1 over 1. So down 1 is my rise. Right 1 is my run. So rise over 1 is negative 1 over 1, which is negative 1. And so there are your 3 parts of part A there. So whenever you have an integral function and they ask for a specific value of that, that means finding the area under the curve. When they ask for the derivative of that, they're asking for the y value of this graph up here, because the graph is the derivative of your integral function. And then finally, when they ask for the second derivative, they're asking for the slope of that graph up there, because the second derivative of an integral function is the slope of your graph, which is the derivative of your integral function. All right. Okay, let's go ahead and take a look then at part B here. So identify any relative extrema and justify your answer. Okay, so let's begin here. H has a relative max when H prime, which we've already said earlier is equal to f of x, changes from positive to negative. Now, where does that happen on our graph? So this is a definition that we learned back in Unit 5. So let's review that really quick. A function has a relative max anytime its slope goes from positive to negative, because when that function's slope goes from positive to negative, you end up with the top of a hill, which results in a peak, which was also known as a relative max. Now, the downside to me drawing that picture is you guys are going to look over and you're going to think, oh, well, there's a relative max. That's actually not correct, because I want you guys to understand this is a graph of f. Yes, that's a relative max on the graph of f, but they're asking about the relative max of h. Okay, and so that's a different story. So h has a relative max when h prime, which is f, changes from positive to negative. And so the question becomes, where does this graph change from positive to negative? Well, the graph, not its slope, not the slope of this graph, but the graph itself. This graph changes from positive to negative anytime it goes from being above the x-axis to being below the x-axis as we go from the left to the right. So as you can tell right here at this point, if I'm moving from left to right, draw some little directional arrows here, you can see that we cross negative 2. We went from being above to being below. And so that is a relative max. So h has a relative max when h prime, which is f of x, changes from positive to negative. And this happens when x equals -2. And I don't see any other places on here. Now, you do have to be careful to look, okay? There might be more than one place. As you can see, this is the only place where the graph is above and then suddenly it's below, okay? Now, the next question that we can address is the relative minimum, because it doesn't say just relative max here, right? It says relative extremus. So we need to look for both. So h of x has a relative minimum when h prime, which equals f of x, changes from negative to positive, the other way. So is there anywhere on this graph where it's below the x-axis and then it changes to becoming above? No, there isn't. Up here, we're above, and then it crosses, and it's below, and after that, it never crosses the x-axis again. It touches the x-axis, but it just stays negative. So it has to change from being positive to negative. It can't stay below. And so in this case, we would say there is none. So I would just say this does not occur. Okay. Now, it's important whenever you're doing these kinds of explanations that you give reference to the function that they're asking about. Like the question is asking us about the function h, right? So you have to reference h in your answer. But you also have to reference f because you're connecting them. We're talking about h, but we're using f to answer our question. And the connection is the fact that f is the derivative of h. So that's their relationship. So this is the function they're asking about, so we have to talk about that. But we also need to talk about the fact that we're using the graph of f, and we connect them by mentioning the fact that f is the derivative of h. So it's important that you guys include this statement here, that h prime is equal to f of x. That's important. You're going to need to make reference to both functions in your explanation. All right. Let's go ahead and move on to part 3 here. All right, part C says identify where h has a point of inflection. All right, so remembering our definitions from Unit 5, you guys know that a point of inflection is where a graph changes its concavity. But how do you know where that occurs? Well, we're talking about h, right? So h, we have to start by talking about h. H of x has a point of inflection when, now at this point you could say when its concavity changes, but you don't need to say that. What you need to say is how you know where the concavity changes. And you know because the second derivative changes sign. When your second derivative changes signs, that means concavity is changing. So h of x has a point of inflection when h double prime of x, which equals what? F prime of x, which we saw in part A, remember, changes signs. Notice I'm not going to say changes from positive to negative or negative to positive. That's not necessary because it doesn't matter. The point is it's a point of inflection just so long as it changes. It doesn't matter whether it's positive to negative or negative to positive. But you could say both. It's just a waste of time. Anyway, so h of x, the function they're asking about, has a point of inflection when the second derivative of h, which is f prime, that's the graph I'm using, changes signs. Now you have to understand what f prime represents though, right? Remember earlier back on part A, we talked about how f prime is the slope of this graph. So where does the slope of this graph change? From being positive to negative or from negative to positive? Well, there's two places where the slope of this graph changes. Okay, the slope of this graph changes here because to the left it's the negative slope and to the right it's a positive slope. And the slope also changes here. To the left we have a positive slope, but to the right we have a negative slope. So there are two places where the slope of this graph
changes. And therefore, that means there's two places where f prime changes. And if there are two places where f prime changes, those are the same two places where h double prime changes. And when h double prime changes, that means the concavity of h is changing, which means we have a point of inflection. So this happens at x equals 0 and x equals 2. Okay, remember, you want to put the x values. I think it's really tempting for people to put -2 for this point because they see the -2 right here. But that's the y value. You've got to remember, you're putting the x value for these points when you say that. Okay. And honestly, I should have changed the way these questions are worded anyway, and I'll do it on your guys' worksheet. I should have put here, to be more specific, identify the x values of any relative extrema of h, and also identify the x values of any points of inflection. There. All right. And the reason for that is because I could ask you guys to calculate the y values. It would just be a little bit more work, but I don't think it's horribly necessary. But the point is, and actually we're going to do that in part D anyway, but I think I'll leave these as just find the x values, and we'll leave it at that. But in part D, we are going to have to go and find those y values, and I'll show you how to do it right now, actually. Let's begin. All right.
All right, so let's go ahead and find an absolute min and max of h here. All right, so to begin, when you're finding an absolute min or max, you're going to want to do the candidates test. And when you do the candidates test, you set up a table consisting of your input variable and your output variable, which in this case is h. And what you do is you're going to put the endpoints in first. So we have an x value on the left endpoint of -3 and an x value on the right endpoint of 4. And then we want to find all the critical values in between. Now, the critical values are places where you may possibly have a relative extrema, which are one of the candidates for the absolute extrema. So to find critical values, we're looking for the place where the derivative of this function equals 0. Now, the derivative of h, as you guys know, will just cancel out that integral and leave us with f. And so I'm looking for places where f equals 0. In other words, where f touches the x-axis. Okay? So this is a critical value, and this is a critical value. So we'll put those in there in order, -2 and +2. All right. So the next thing that we got to do to find our absolute extrema is to actually find out what the y values are, because when we're looking for extrema, we're wondering what the greatest y value is, or what the greatest or the least y value is. So let's go ahead and do this. So for the first part here, if I were to take my h function and plug in -3 to it, we would end up with the following integral. Now, anytime your integral has the same number on the top and bottom, we have a property for that, and it's 0. Okay, so that one's nice and easy to calculate. Let's move on to the next one there, h of -2. Now, this one we would actually have to work out a little bit, but we actually already did it, if you guys don't recall, back here on part A. We found that earlier, and we found that to be equal to 1/2. So I'm just going to steal my answer there from part A for that instead of recalculating it. All right, let's go ahead and move on to the next one here. And now I want to find out what h of 2 is. Now, this is the one where I'm actually going to have to work for it a little bit. The first two are kind of easy. The next two are going to be a little bit more work, okay? So basically, to find the value of this integral, that's just basically the area from -3 to 2. So I need to find a couple of area pieces here. Starting at -3, my first area piece I see here is a little triangle. My next area piece is a bigger triangle. My next area piece is what I've been calling a ramp. And that's where I'll stop because we're going to 2. So we're only going from -3 to 2. So here's -3, here's 2, and that's where I stop. And basically, I just need to find all those little areas of each of those shapes and add them up. All right, so we've already found the area of this one earlier. We found out that was 1/2. Let's go ahead and find the area of this triangle here. Now this triangle, the area of a triangle is 1/2 base times height. Okay, so my base is 2 spaces long, and my height is 2 spaces long. And so 2 times 2 times 1/2 is 2. But we have to remember it's under the x-axis, and therefore this area is going to be -2. All right. Next, we want to find the area of the ramp. And that ramp, we've talked about many times how to find those areas. The first thing I'm going to do is I'm going to find the area of this square. And then what I'm going to do is I'm going to subtract from it a quarter circle. And that will leave me with the area of the ramp. So the square minus the quarter circle will leave me with the ramp. Okay, so that square that I traced out there was 2 times 2 in its area, which is 4. The quarter circle, this piece right here, has a radius of 2. So the quarter circle has an area of pi r squared. And since it's a quarter circle, we divide it by 4. And I end up with 4 minus 4 pi over 4. The 4's cancel, and I'm left with 4 minus pi, and that would be the area of that ramp. Okay. So now I've got 4 minus pi, but we got to remember it's under the x-axis. So what happens is the 4 becomes negative and the pi becomes positive. You're going to switch their signs because it's under the x-axis. So -4 plus pi. Okay. Now that I've done all my geometry, I'm ready to move on to actually answer the calculus question now, which is what is the integral from -3 to 2? In other words, the area from -3 up to 2. That would be 1/2, the little green triangle, plus -2, the pink triangle, plus -4 plus pi, the ramp. And all we got to do is put all that stuff together. Matter of fact, this is an FRQ question, so if you wanted to, you could just leave it like this. But that's going to be difficult because later on we do want to know what the biggest x value and the biggest y value is. So we should probably put these together. So let's go ahead and do that. So we have 1/2 minus 6 plus pi. Now I want to subtract these things a little bit. So we have 1/2. Let's think of that maybe as a decimal might be easier. 0.5 minus 6 plus pi. Now 0.5 minus 6, that's going to be -5.5. And I'm adding to that pi, which is about 3.14, right? So let's go ahead and figure out what that would be. Since they're opposite signs, we're going to be subtracting them. So it's about 2.36, and since the 5.5 was the one that was actually negative, it turns out the answer is negative. So that's going to be -2.36 approximately. Right there. Okay. Let's go ahead and do the last bit there. One more piece. Now I want to find out what is h of 4. So that means we're going from -3 to 4. Okay. So that means I want to find the area of everything that I just did plus this blue section here now. So I need to add all these together again. Now, I already know the answer for those first three, right? For the green plus the pink and the purple regions there, we already got that answer back here when I did 2. It was -2.36, right? So why reinvent the wheel? We can just leave it like that, right? But now I want to add on a new piece, and that's this last piece here, the blue piece. Now, you may notice that this blue piece is the same thing as this purple piece. They're symmetrical. And so it's also -4 plus pi. So we have -4 plus pi. And so we'll just go ahead and put all this stuff together here. So first of all, if I put -4 with -2.36, I'm going to get -6.36 plus pi. And pi is 3.14, so I'm going to go ahead and combine those now. So since they're opposite signs, we are going to end up subtracting those. And since the 6 is the bigger one, the answer comes out negative. So it's -3.22. Okay. Now you guys might be thinking, Mr. Bailey, can I just use a calculator? Maybe, maybe not. You got to be prepared for either way on your exam. Quite honestly, this would probably be a non-calculator type question on your AP exam. There's no reason why you guys shouldn't be able to add numbers and decimals together. So it wouldn't be unfair for them to expect that from you. All right, so we're ready to identify our minimum and our maximum now. This appears to be my minimum. My maximum value appears to be this half right here. And there's my final answer for that one. Now this thing does say justify your answer, but for these types of questions, this qualifies as a justification. You should really have your work shown also, all the work I've been showing, but for now, just know that the work you show is your justification. You don't have to write any sentences out or anything like that on these types of questions. All right, let's go move on to the next one.
All right, last question. I just tossed this one in here because it's a pretty common question on, well, it's not that common. I've just seen it occasionally in AP exams. We have an integral function here, but it's a little bit more complicated than our typical integral function. It has an integral here, but it also has another part that's not in the integral. So not a huge deal. I'll share with you how to do it. So let g of x be equal to x squared plus the integral of f prime of x dx. Find g prime of -3. All right. So first of all, I want to find g prime. So that means I'm going to take the derivative of all this stuff. So when you take the derivative of that, you're going to get 2x. And when you take the derivative of this, the integral is going to cancel and that x is going to drop in. So that's going to give me f prime of x. Okay. Now I want to find g prime of -3, so I'm going to plug it in. So this is -6 plus, how do I find that? Well, if this were just an f, that would just be the y value of this graph. But since it's a prime, what they're asking for in this case would be the slope of f at -3. But -3 right here, the slope is down 1 over 1, so it's -1. And so the final answer here will be -7. Now, I'm not too sure if I'm not too sure if yours on your test I'll put a prime here or not. But it's important that you recognize the difference. Okay? Since there's a prime here, when you take the derivative of this integral, you're left with f prime here, right? And you have to understand that means the slope of this graph. But if I had written this question slightly differently, like let's say I wrote it like this instead, just an f without the prime, you would get a different answer, okay? You would still get 2x here, but here you would get f of x. And so when you plug your number in, you would still get -6 here, but this, if you were to plug in -3 here, that would be, you're looking for the y value at -3, which is a positive 1. And therefore your answer would have come out to be -5 instead. You've got to pay attention to those subtle little details there. That prime changes the game. So whether or not that prime's there is going to determine the outcome. So, but the point is that aside from paying attention to those little details, how do you do the problem? You find the derivative first. For whatever's outside the integral, just take the derivative like normal. For whatever's inside the derivative, just apply the second fundamental theorem of calculus. Drop the integral, plug in the x, and you're good to go. Finally, plug in your number to your expression that results from that and evaluate. Be careful that you know f means y value on this graph and f prime means slope. All right, so that does it. We'll stop there and hope that was helpful, and we'll see you guys in class.